Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 4, Lesson 8 on the circumcircle and its center. What in the world's a circumcircle? Well, before we get into that and how to find its center, we need to talk about something else. All right, points of concurrency. When three or more lines or line segments intersect at a common point, it's known as a point of concurrency. There are many special types of these points related to triangles and circles. Now, you might wonder about why three or more lines, why not just two lines? Well, anytime two lines intersect, that's just an intersection point, all right? But if I've got three lines, in this case M, N, and P, that all share a common point, it's called a point of concurrency. And again, there's some very important points of concurrency when it comes to triangles. And we're going to see the first one in this particular lesson. So let's get right into it in exercise number 1. Given triangle ABC shown below, do the following. Letter A, construct the perpendicular bisector of segment AC. All right, now today's lesson is going to be all about the perpendicular bisector construction. If you can do that, then you're going to be able to do what we do today just fine. So let's review how you construct the perpendicular bisector of any line segment. And of course, we'll start with line segment AC. Here we go. All right, so the first thing I'm going to do is I'm going to take my compass, I'm going to put the sharp point at either A or C. In this case, I'm going to put it at A. And then I'm going to set the radius of my compass to be longer than half of the length of AC. All right, it has to be more than half the length. And I really want the point right on A. All right, that's good enough. Anyway, I am now going to draw an arc up here. I'm going to try to draw an arc up here. I'm going to rotate it down and draw an arc down here. Okay, now what I'm going to do is, without switching my compass length, I'm going to put the tip of the compass at C, and I am going to draw those two arcs again. Ooh, just barely got that one. And now the X's mark the spot. I'm going to bring my straight edge over, and I'm going to draw a line segment that goes through, or a line that goes through those two intersections, and that is the perpendicular bisector of AC. All right? So again, very, very simple. Just as a reminder, right, what we're doing is we're locating a point up here that's equidistant from A and C. We're locating a point down here that's also equidistant from A and C. Therefore, both that point and that point must lie in the perpendicular bisector of AC. So when I draw the line through the two of them, I have drawn the perpendicular bisector. All right, let's talk about letter B. I think I already kind of gave the answer away, but let's talk about it. What does the line from A represent in terms of point A and C, right? Well, what does the perpendicular bisector always represent in terms of the endpoints of a line segment? It represents all points that are equidistant from the two endpoints, right? So all points equidistant from A and C. All right, so every point that is the same distance away from A as it is from C lies along that line. Just kind of, put that away for right now. Letter C, construct the perpendicular bisector of segment BC. All right, well, since again, this is a very important construction for everything that we do today, let's do it again together. All right, so I'm going to bring this thing up. Again, I'm going to do the perpendicular bisector of segment BC. So I'm going to put the pointy end of my compass at either B or C. I need to make the length of my compass's radius more than half the length of BC. So now I will draw one arc, another arc. All right, I will then switch so that the point is at C, but do not change the radius length at all. If I don't get this right on C, the end result of my construction is going to be terrible. So I want to make sure I do it as well as I can. Oh, I just barely made that one. And I missed that one altogether, so I'm going to have to like go back and make that up. But that's okay. Since I haven't changed my compass length, I can do that. Put this back at B. That sometimes will happen to you as well as me, which is that your two arcs just don't intersect each other. Of course, it didn't end up hitting the other arc. That was gorgeous and makes me a little worried. But we'll live with it. So now we're going to draw a line segment that passes through those two. And that, in theory, is the perpendicular bisector of BC. All right, great. So let's take a look at letter D real quick. Label the intersection of the lines drawn in A and C as point M. Explain what the line from C represents in terms of point B and C. All right, so a couple things here. I'm just gonna draw this in, right? We'll call that M, all right? And now, what does the line that we just constructed represent in terms of B and C? Well, that's easy. That's the same question that we had up here in letter B, right? In other words, that is all points equidistant from B and C, right? So the perpendicular bisector of any line segment represents the collection of all points that are equidistant from the two endpoints of the line segment. Okay, great. So just for a moment before we move on, right? This particular line, right, the perpendicular bisector of segment AC represents all points that are equidistant from A and C. This line segment represents all points that are equidistant from B and C. And then we just happen to have their intersection point M. Great. All right. So let's take a look at letter E. Why must point M lie also on the perpendicular bisector of AB? Construct that bisector to verify, right? So I claim, without even constructing the perpendicular bisector of segment AB, that point M, that point must lie on it, right? Pause the video now for a second and think about why that must be true. All right, well, think about this just for a minute. Point M lies equidistant from A and C. What's that distance? I don't know. Let's say it lies 2 inches from point A and from point C. Well, M also lies equidistant from point B and point C. So that would mean if it lies 2 inches away from C, it would also have to lie 2 inches away from B. But that means that point M must lie equidistant from point A and point B, which means it must lie in the perpendicular bisector of AB, right? So it's equidistant from A and C, it's equidistant from B and C, which means by default it must also be equidistant from A and B. And that's what we want to write down, right? So it lies equidistant from A and C and equidistant from B and C, so must lie equidistant from A and B, right? And again, just think about it. It's really kind of cool, right? If I were to just sort of like draw those in, again, I'm not going to because I don't want to make the picture look worse than it is, but pick any number you want. Maybe M lies 6 centimeters from A, therefore 6 centimeters from C. But if it lies 6 centimeters from C, it must lie 6 centimeters from B because it lies on that particular line. But then if it lies 6 centimeters from B and 6 centimeters from A, it's got to lie in its perpendicular bisector. Now, if I've done a really good job with my first two perpendicular bisectors, then when I draw the perpendicular bisector of AB, it will go directly through M. Let's see how good of a job I've done. All right, here we go. Oh boy, this is the moment of truth every time. Moment of truth on these. So I'm going to do the perpendicular bisector of AB. So we will do what I've been doing, which is make that compass a little bit more, or just more than half the length of AB, and move my irritating ruler out of the way. Still not on point A. There we go. Okay, now make another arc here. All right, switch it around, put the point of my compass on B. Hope against all hope that when I draw these two arcs, it gets the job done. It's definitely not going to be too bad. I don't know if it'll be right on the money, but we're going to try. All right, and rotate. Oh my goodness. Oh, this is looking good. Look at that. All right, maybe not perfect, but pretty darn close, right? Now, to loop back, right, this is a point of concurrency, right? The three perpendicular bisectors of the three sides, or the perpendicular bisectors of the three sides of any given triangle, right, will all intersect at the same point. And again, it's really remarkable, right? It doesn't seem like that should have to be the case. But if you're equidistant from 2 points and then equidistant from another 2 points of the triangle, then you have to be equidistant from the last 2 points on the triangle. You have to be. Now, keep in mind what this means is that the distance from M to A is equal to the distance from M to C, which is equal to the distance from M to B, and this finally brings us to what's called the circumcircle. Let's take a look at letter F. Draw a circle with M as its center that passes through each of the vertices of ABC, right? Now keep in mind, right, the whole point of a circle is that it's going to be, right, a curve where all the points along the curve are the same distance away from the center point. But that's exactly what we have with these three vertices, right? Every one of these three vertices is the same distance away from point M. And again, if I've located point M properly, then what should happen when I create this radius and when I create this circle is that it should intersect all 3 points, all 3 vertices. And as you can see, it's close, and if I adjust it just a little bit, it's perfect, right? So in other words, a circle centered at that point, which is called the circumcenter, right, will always then produce a circle which goes all the way around the triangle and intersects the triangle at its 3 vertex points. It's really kind of cool, right? So let's kind of summarize this all. The circumcircle, right? And a better picture of that thing that I just drew, a little bit better here. Let's talk about the circumcircle and the circumcenter. The perpendicular bisectors of each side of a triangle have a common intersection point, a point of concurrency, known as the circumcenter of a triangle. This point is equidistant from all 3 vertices and is the center of a circle that circumscribes the triangle. So the word circumscribe means to surround, to circumscribe. And you know, obviously there's a lot of words here that are similar to the word circle, right? Circumscribing, right? When you circumscribe something, you surround it, all right, by another shape. And so every triangle has one unique circumcenter and then one unique circumcircle that goes around the triangle and passes through each of the triangle's 3 vertices. And it's at the intersection point of the 3 perpendicular bisectors. Hold on. Just got to make sure of this. There we go. I knew there was another problem on that. Let's take a look at exercise number 2. For triangle EFG, the perpendicular bisector of segment EG is drawn. Locate the circumcenter and draw and circumcircle for this triangle. Well, there's a little mistake. Locate the circumcircle and draw the locate the circumcenter and draw the circumcircle for this triangle. Ugh, couldn't quite get that out. Label the circumcenter as point C. Now, what's really cool about the circumcenter, right, is it's the intersection point of the 3 perpendicular bisectors of the 3 sides. But we don't have to draw all 3. We just have to draw 2 of them. Because if we draw 2 of them and find their intersection point, drawing the 3rd one would just go through that intersection point. We did it in exercise 1 simply to verify that it was true, but we don't have to do it in general. We really only have to draw 2 of them. And the cool thing about this problem is that one of them has already been drawn. All right? We just have to draw the perpendicular bisector of either EF or GF, and wherever that perpendicular bisector intersects the one that's already drawn is our circumcenter. So let's do this one again together. All right? I say we draw the perpendicular bisector of segment EF. All right? So I'll just move my ruler out of the way. All right, let's draw the perpendicular bisector of EF. And again, if I don't get this pretty accurate, then my circumcircle will be pretty bad. So I'm going to try to be kind of careful here, which I should always try to do, but in certain constructions, it's more important than in others. I already feel like I'm a little bit off, but we'll take a look. We'll be able to tell very quickly how on or off I am. All right. So we just do that perpendicular bisector construction. All right, X marks the spot, so I can now connect the 2 intersections with a line or a line segment. Okay, excellent. Now, just wanted to mention again, right, I could definitely construct the perpendicular bisector of segment FG. But because this is a point of concurrency, that perpendicular bisector would go right through it. So that's our circumcenter, and we're going to label it as point C. All right. Now we want to draw the circumcircle. All right. The key is the circumcenter is the center of that circle, and it's equidistant from point E, G, and F. So I can use any one of those 3 points as my radius. And it probably makes most sense to use point F, although you never know. Again, that looks pretty good. Let's see how accurately I found my circumcenter. Not too bad. All right. You can really tell how good your construction skills are by how closely this circle is to those 3 vertices. And again, how cool is that, right? If I've got 2 perpendicular bisectors, they will intersect at the circumcenter of a triangle, and then I use that as my center, and then a radius that has a length of anything from that center, the radius is from that center to any one of the 3 vertices. All right, let's keep playing around with the circumcircle and its center. Now, the location of the circumcenter. In our first 2 examples, the triangle circumcenter was located inside the triangle, but that's not always the case, okay? And it probably seems a little bit weird that it wouldn't always be the case, but you can have a circumcenter that is located outside of a triangle, all right? Let's take a look at that in exercise number 3. For triangle QRS, construct the circumcenter and circumcircle. Leave all construction marks. Mark the circumcenter as point T. All right, cool. Well, remember, I just have to construct 2 perpendicular bisectors and find their intersection points. Now for me, I find it easier to create the perpendicular bisector of longer segments than I do of shorter segments. So my natural inclination is to construct the perpendicular bisector of QR and construct the perpendicular bisector of SR and find where they intersect each other. I think what we'll do is maybe together, let's construct the perpendicular bisector of QR, and then we'll have you construct the perpendicular bisector of SR to find that intersection point. So let's do QR together, all right? That one's a little bit more challenging because it's all tilted or angled or whatever. So here comes my perpendicular bisector again. I told you this particular lesson was going to be all about that. All right, so again, let me try to be as accurate as possible. Still not quite on cue. It's not bad. I'll take that. Drifts. All right. Let me get rid of that. Bring it down here. Bring this up. Another arc there. Bring that up. Switch it around. This gets to be kind of a boring construction after a while, but it is what it is. Oh, just barely caught it that time. This one's a little bit better. Okay, so put that away. Move this up. And let's get that perpendicular bisector. Now, one of the tricky things about a situation where the circumcenter doesn't lie within the triangle is that you may have to really extend that perpendicular bisector. It might have to go a ways, okay? So there we've got our perpendicular bisector. Awesome. Now what I'd like you to do is pause the video now, and I suppose your choice. I'm going to do the perpendicular bisector of SR, but you could do either SR or QS, and then wherever it intersects the line that we just drew is our circumcenter, and it should end up being outside of the triangle this time. Pause the video and see what you can do. All right, let's do it. So here we go, SR. I'm not going to do QS, I'm going to do SR because it seems like it's the easiest thing. So put my compass at R. Again, get a nice long arc there. All right, just got to keep in mind which arc is which, and that can get very tricky sometimes, right? Because these pictures can get quite involved. All right, and of course I've got to like go back and forth on my screen. Okay, let me put it on S. Oh, I like it. Still kind of near S. And rotate it down. Okay, X marks the spot. We'll come back to you in just a little bit. All right, and I need to connect this with that. Not too bad, a little bit off, but hopefully it won't make it absolutely terrible. We'll see. And right there is going to be my circumcenter. Did they tell me what to label it? Yep, that's supposed to be labeled as point C. So there's our circumcenter, and it lies outside of the triangle this time. And again, moment of truth. Now I'd like to draw the circumcircle, right? T is going to be the center of the circumcircle. So let's bring the pointy end of our compass over to point T. Let's extend it out, maybe to point R. Whoops. There we go. That's pretty good on point R. Whew. Let's hope. Here we go. Oh, missed point Q and point S pretty severely. Or at least it appears that it did. All right, not too bad. But any little kind of errors, right, in terms of where that intersection point is gonna then throw that radius off, which then throws everything else off. But it's pretty close, right? And you can imagine, had this been completely accurate, the idea that the circle would pass through R, S, and Q. All right, now I know we've only done, this is only our third example, but let's generalize, right? And I bet this won't come as any great surprise to you. Let's take a look at exercise number 4. Fill in the following. For an acute triangle, the circumcenter will lie blank the triangle, and for an obtuse triangle, the circumcenter will lie blank the triangle. So, what do you think? Pause the video now and see if you can fill those in. All right, well, our first two examples, we were working with acute triangles and the circumcenter would lie or lied inside the triangle, right? So it lies inside the triangle. And an obtuse triangle, which we just did, that will lie outside the triangle. And it's that simple, right? So if you've got an acute triangle, i.e. a triangle where all the angles are less than 90 degrees, then the circumcenter will lie inside of the triangle. Those were exercise 1 and exercise 2. And if you even have a single obtuse angle, quite frankly, you can't have two obtuse angles, but if you have an obtuse triangle, which is any triangle with an obtuse angle, right, then the circumcenter will lie outside of the triangle, which is what we saw in this situation. All right, now there is one final case though that we have to look at. The circumcenter of a right triangle. Now, the circumcenter of a right triangle lies in a very convenient location, and let's try to figure out what that is by playing around in exercise number 5. Let's take a look. Our final consideration is the circumcenter of a right triangle. Do the following for a right triangle EFG shown below. Letter A, locate the circumcenter of the triangle, label it H. All right, so what I'd like you to do now is pause the video, okay, and construct two perpendicular bisectors. You could either construct the perpendicular bisector of EG and GF, or GF and EF, etc. I think I'm going to actually, me personally, so if you want to do what I'm going to end up doing, I'm going to construct the perpendicular bisector of GF or FG, whatever. And I'm also going to do one for EF, just because I like dealing with that longer segment. Pause the video now and go ahead and try to locate the circumcenter of the triangle. Now, if you did it correctly, right, you probably found something that wasn't too much of a surprise, keeping in mind that if you have an acute triangle, the center should have been inside the triangle, but this isn't acute. And if you have an obtuse triangle, it should be outside the triangle, but this isn't obtuse. So what did we find? Well, okay, let's first construct the perpendicular bisector of GF. That's got to be relatively easy, right? Nice horizontal line segment there. All right, that looks good. Let's do that. And let's do that. Okay, let's switch. And let's do that. And that. And let's now draw that perpendicular bisector in. Fantastic. Oh, not so fantastic. That wasn't supposed to happen. That's a little bit better, okay. And now let's do the perpendicular bisector of EF. Now it wouldn't make any difference again whether you do EF or EG, right? Those should be the same. But you never know. Okay, so again, let's open it up. More than half the length. That looks good. And again, I really want that point right on E. I'm not sure that's right on E, but it's as good as I'm going to get for right now. Okay. Bring it up, switch the location of my compass point, put it on F. And I think I'll just take that little shortcut. And now let's draw in that perpendicular bisector. Okay. There we go. And look at that. point H falls on the hypotenuse. Huh. Point H falls on the hypotenuse. Now let's take a look at letter B. You should have found that the circumcenter fell on the hypotenuse. What special point on the hypotenuse is it? All right, so in other words, point H doesn't just fall on the hypotenuse. It falls on a special point on the hypotenuse. What point on the hypotenuse is it? Pause the video now, and don't forget, right, that we constructed the perpendicular bisector of the hypotenuse. So pause the video and write down what you think it is. Well, it's the midpoint of the hypotenuse, right? So this is the midpoint of the hypotenuse. All right. And the last little piece, draw the circumcircle. All right. Well, why don't you go ahead and draw the circumcircle, and then I'll draw one as well. Pause the video now. All right, well, let me get rid of my ruler, given that I do not need it anymore. Thankfully, I just need to extend again so that I have a radius that is that long. And it's really, you gotta really have a real compass, not just an electronic one. All right. Not too bad. Not too bad. Look at that, right? Nice circle, goes all the way around the triangle, intersecting at E, G, and F. And in fact, EF, right, is a diameter of that circle, right? Because it goes all the way across the circle and passes through the circle's center, which is point H. And this brings us to the last little fact, right, about circumcircles, which is that the circumcenter of a right triangle will always be the midpoint of its hypotenuse. And it kind of makes sense. Not so much that it's the midpoint of the hypotenuse, but the fact that it must lie somewhere on the triangle. Because keep in mind, right, if the triangle was acute, the circumcenter would have to lie inside. If it was obtuse, it would have to lie outside. And so if it's a right triangle, it should lie right on the triangle somewhere, and it just so happens to always lie at the midpoint of the hypotenuse. All right, let's summarize. So what we saw today was something pretty complicated and something pretty cool as well, right? Which is if you draw the perpendicular bisector of each of the three sides of a triangle, right? Those three perpendicular bisectors will all intersect at a common point, which is known as a point of concurrency. That point will be equidistant from all three vertices of a triangle, and therefore you can draw a circle with that as its center that then passes through the three vertices of a triangle. That point is called the circumcenter of a triangle, and that circle that encloses the triangle is called the circumcircle of a triangle. All right? Every triangle has a unique circumcenter and unique circumcircle, which can be found not by drawing all three perpendicular bisectors, although it certainly could, but by simply finding the intersection point of any two perpendicular bisectors. All right, this is one of the most famous topics in all of classic geometry, so get some practice with the constructions, but also make sure to just understand what's going on here with all these equidistant kind of notions and points of concurrency. Ooh, that's hard to say. All right, for now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.